All right, so now we're going to talk about how you can use this depth-first search algorithm to answer questions like whether or not a triangulation is orientable. Okay, so we can determine orientability by sort of traversing the triangulation using this depth-first search algorithm which we talked about. And then each time you visit, well, the first time you visit a node, you assign some sort of compatible orientation. And if you happen to revisit the node again, you check whether or not that orientation is compatible with the one which you have. So assigning a compatible orientation to each new triangle. We encounter. And then visiting each of the adjacent triangles. So if you encounter a triangle which has already been visited and therefore already has an assigned orientation, then you have to check whether it's compatible. Okay. So if we encounter a triangle which has already been visited, and therefore has an assigned orientation, right, then we check if it is compatible with the, the orientation of the triangle you're visiting from, basically. Okay, so let me sort of describe. It's like the code. It's like for this, right? So you have a Boolean sort of return, right? So it returns true or false. It's like to the question of whether or not this thing is orientable. And you started by first specifying, you know, it's like a triangle with a prescribed orientation. Okay. So if mu is unmarked, that triangle is unmarked, then obviously you want to mark it. Okay, and then you choose an orientation containing I. So what do I mean by that? Okay, so what I mean by that is that if you recall, it's like there are these 6 possible permutations. It's like of the ordering of the vertices for any triangle, and they correspond to 2 different sets of orientations, more or less having to do with whether the vertices are ordered in some sort of clockwise versus anti-clockwise fashion. Okay, so what I mean by this is that you know, I is one of those 6 possibilities, and you just want to choose an orientation which is, you know, one of the 3 which is in that equivalence class which has the same orientation. Okay, all right. So once you've done that, then so this thing here, it's like would be what we call P1, of course, in this depth first search algorithm. And then now you want to look at all the adjacent, it's like faces. Okay, so this can be done explicitly because of the way this is structured. So I'm going to say Bx is equal to is orientable. And then what I'm doing is I'm going to call this routine recursively for the face or the triangle, which is which shares the same leading edge. It's like as this triangle with this particular orientation. Okay. Actually, not really, because I'll first flip it. I'll look at the symmetrized version of this. And the reason why I do this is because if you recall, when you have triangles which have the same orientation like this, right? The induced orientation on the triangles are reversed, if you will. All right. So, sorry, the induced orientation that's like on the faces are reversed. So that's why you flip it with this operation. Okay. Yeah. So you flip the ordering. Okay. So that's basically why you do it that way. Okay. So this sort of says, well, I'll look at the face which is adjacent. Sorry, I look at a triangle which has this leading edge as an edge as well. Okay. And then I do the same thing. It's like, but now for the other, it's like the other edges of the triangle. So do by is orientable. And so, okay, so I still have to apply this sim operation to flip the edge, okay, the leading edge. But then I want to go to the next face of the triangle. So that's, that's E next, right? That's the E next operation. And then I want to know what is the face which has, this next face, sorry, the triangle which has the next face, it's like as a common face, right? So that's F next. Okay. Okay, all right. And then BZ is the same thing. So it is orientable, F next. And you apply this E next twice. So just note that by E next squared. Okay, symmetrized mu I. Okay, that's probably what. Okay. All right, so this tells you more or less that, so this sort of says, well, okay, can I orient the adjacent triangles in a compatible fashion, right? And that sort of actually recurses in the depth first search way. It's like all the way out. Okay. So again, the question of whether or not things are orientable has to be that, all the adjacent triangles, it's like can be oriented in a compatible way. Okay, so I return sort of Bx and By and BZ. So this will only be true if each of these things are orientable, basically. Okay, else you, okay, so else happens when mu is already marked. So that means there's already an orientation. Okay, else you have to check whether or not the orientation, it's like which is sort of being suggested to you is compatible to the orientation you already have. So you return the question of whether or not the orientation which you already have of mu, right, contains I. And again, if you recall, it's like what this means is that there's, there are these 6 possible permutations, right, and then there are 2 sets of 3 which each correspond to the same orientation, right? So there are 3 of these I values, it's like which in some sense induce the same orientation. You just want to check that the orientation you have here is compatible with that. So for example, if I was 0, then you would be okay if the orientation you've already assigned to mu is 0, 1, or 2. And if I is, say, 4, then it would be okay if the orientation assigned to mu was 4, 5, or 6. Okay? All right. Anyway, so if that's all true, it's like then you end the if statement. Okay? So this then gives you, it's like a recursive, it's like routine, it's like which does this depth first search, it's like approach where you try to label, you try to assign the orientations. It's like from, it's like triangle to triangle in a locally consistent way. And then it's like what happens, of course, is that at some point in time, it's like you'll come to a triangle which you've already assigned orientation to, and you just want to make sure that the orientation which has already been assigned is compatible with what you would like to assign it with. Okay, and if that's the case, and if you can always do that, then you have something which is orientable. And if you find that there is this mismatch between the orientation which is already there and what you would like it to be, then that's basically meaning that you can't you can't choose this globally consistent orientation, and as a consequence of that, the the surface is not orientable. Okay. All right. So what will so this again gives you, it's like it answers the question of whether or not it's like a triangulated, compact, connected two-manifold without boundary is orientable. And what we'll see later is that we're also going to compute the Euler characteristic, because as you recall, if you know both the Euler characteristic and whether or not the surface is orientable, then you can uniquely classify all compact, connected two-manifolds without boundary. Okay, so let me stop here.